health. And specifically, his group develops methods and systems to automatically analyze human activities to address challenges related to healthcare. And he has been serving as area chairs for the top vision AI conferences like CVPR, ICCV, ECCV, and ICAI. He was also co-recipient of the Best Student Paper Awards at the Mobile Health 2014 and IEEE Face and Gesture 2015. And his work was covered by MIT Tech Review, Wild UK, New Scientist, BBC, and Forbes. And so, as usual, if you have any questions during the talk, feel free to drop your questions in the chat channel, and Professor Lee will go ahead and address them when available. Okay, so yeah, Professor Lee, so please feel free to take over the stage whenever you're ready.
Sure. So thanks for the introduction, Jacob, and very nice to have this presentation. So in today's talk, I'm going to talk about some of our recent work, some of our early work and very recent work. So learning visual knowledge from held image and text data. Now, before we sort of start our talk, let's really look at an image. So this is an image I took from actually the Arizona State ASU website. So it's not totally clear what is actually happening here. And by the way, I do want my talk to be a bit more interactive because we have this advantage of being virtual. So I think, if you have any questions, feel free to just post that in chat box, or just ask that directly. I don't have an easy way to see the chat box because I only have a single screen. So if you have any questions, just ask that directly. Let's look at this. Let's go back to this example and really try to ask this question: what is happening in this image? So you see this, dark image looks like some sort of cave, and you see this sort of mechanics or a vehicle, right? But it's not totally clear what's inside of this image. If you want to give a try, you can try to describe this image in the chat box. For those of you who actually see the recent news from Arizona State University, here is the caption of this image, right? Now, it turns out this is about 3,000 meters under the sea level, and this remotely operated vehicle called Hercules is exploring the seafloor and looking for something called a hydrothermal fluid vents. Okay, now if you look at this caption and let's look at this image and trying to make sense of it. So obviously, this vehicle here is this remotely operated vehicle Hercules, right? And here, this is the seabed that the vehicle is exploring. And these weird-shaped rocks might be the hydrothermal fluid vents. Right? If you're trying to make sense of this image here. Now, it turns out on the same web page, there's another image trying to explain what is this hydrothermal fluid vents. Right? So these hydrothermal fluid vents are like little chimney, which is amazing, that is produced by the interaction of the cold seawater and the hot rocks. Right? So that form this weird-shaped rocks, and that's the same thing as shown in the picture here. And this is really amazing research done by Arizona State, and I would encourage you to give this a read. So I hope this example helps to convince you that we are, today living in this internet age. Well, there are tons of images over internet that comes with their text descriptions. Now, as a matter of fact, for every 60 seconds, there will be about 140,000 images being uploaded to Facebook that will generate over 500,000 comments from its users, right? So we're probably already 5 minutes into my talk. So that means we have about 300,000 images being uploaded during the course of my talk and generates about 2.5 million of comments in free form text format, right? Now, the data is here is freely available in great abundance over internet. Now, the question is, what can we learn from these image and text data, right? In particular, what can we learn from those images and their paired text descriptions? Now, as a vision researcher, I'm primarily interested from the vision perspective. So I would like to slightly modify this problem and ask, what can we learn in terms of visual knowledge from these image and text pairs? So in today's talk, I'm going to sort of describe 3 of our works, sort of learning from these paired image and text data. To begin with, I'll talk about some of our early work, learning to localize phrases from image text pairs. And moving forward, I'll talk about some of our very recent, actually ongoing work in terms of detecting scene graphs from image text pairs. And finally, I'll switch gear and talk about how we can generate these controlled and grounded image captions using the scene graph that we learned from the image text pairs. So without further ado, let's dive into the first component. It's going to be quite short. It's really some old work. So this is back about 5 years ago when I was still in grad school, and my friend and I were thinking about this problem, right? So now we have this nice image here. We have the text description associated with this image. So we want to figure out what are the image regions that are corresponding to the tokens within the sentence? And in particular, those image regions corresponding to the phrases within the text description. So for example, so here, this pupil region is what we call the file pit, right, in the text description. So that's the setting of what we call visual grounding of phrases, sometimes known as phrase grounding or phrase localization. The basic setup is that the algorithm is presented as presented with an image and its text description, and is tasked to localize the phrases within the text description within the image in terms of a bounding box of image regions. So what we do at that time is that, let's assume, to simplify this problem, let's assume during training, we actually know the ground truth correspondence. We know that this green box corresponded to a file pit. Just one short moment of, okay, this works. Okay, so let's assume we know this, and now what we're going to do is really trying to learn some sort of function that allow us, I think that's my email, but let's bear with that for now. So, so what we're trying to learn is some sort of function that allows us to map a image region to a text phrases, right? So what we're going to do is we're going to learn a score function that take a pair of image region and the text phrases and really output their similarity score, right? So here's the key idea of how we're going to learn this function. We're going to gather all the image regions, right? So here we have possible regions that are sort of close to the ground truth bounding box of the phrases, and we also have negative regions that are randomly sampled within this image. Now the key intuition is that we can have a positive image region and text phrases pair, and we can have a negative pair, right? Now the idea is that the distance between the corresponding image region and the text description should be smaller than the distance between an arbitrary image region, between the pair of the arbitrary image region and the text phrases, right? So here we can, for example, plug in a random background region so that our sort of ground truth pair should have a smaller distance, or we can plug in a or we can plug in a negative phrases here, right? So that's a key idea. So now the key idea is to encode this sort of matching into a ranking loss, which happen to have this form of a hint loss, so you convert that sort of triple ranking problem into the minimization of a hint loss. And what we're going to do is that, so we're going to train this two-branch network, right? So we have X as image regions, Y as the text phrases. We're going to train this network that project, sort of independently project those image and text data into some latent space. So, and then we're going to compile these data on the latent space and impose our ranking loss here. So we have a question from the audience, which is an interesting question. The question is, the number of positive pairs are much smaller than negative pairs. How do you choose the negative regions to balance your training set? That is a wonderful question. The short answer is we do some sort of hard negative mining. So we select those sort of hard negative triplets into the training process. There has been a very active research field trying to figure out what's the right recipe for this triplet ranking loss in terms of negative, selecting negative samples. I hope that I answered that question. And more recently, when we figure out that if we can get rid of this ranking loss to use some sort of more recent contrastive loss, then the contrastive loss will be able to adaptively select all the hard negative regions. All right, so let's move on. So what are we going to do once we learn this sort of simple network, right? So at inference time, suppose we're given an image and its text description. We're going to extract object proposals from image. We're going to pass sort of text phrases from the image captions. And then we're going to match these image regions to the text phrases using the network we just learned. Now, again, we're going to project them into the latent space and directly measure the similarity score in that latent space. So here are some of the results. These are really primarily qualitative results shown in this slide here. We're able to identify sort of both of these phrases and ground them into the corresponding image regions. So this really works pretty well, given that this is a very strongly supervised model, right? Now, the question is really, what if we don't have these localized phrase during training? I think that's a more interesting question because we know that labeling these localized phrases is quite expensive, while just getting the image captioning can be quite easy, right? Now let's consider the setting that we have this image here that have multiple objects interacting in a certain way, and we have a text description, a group of children playing on the street, some on bicycles, one on a scooter, and one with blue shirt working. So now what happened here is that now if we put the image on the left-hand side and then put all the phrases we pass from a sentence on the right-hand side, right? Now we know that there are a certain number of concepts happening in this image, right? So we have a group of children, we have street, we have some children, bicycle, and scooter, and so on and so forth. And now,
Pero papi,
so now the question is, for the image on the left-hand side, there are tons of regions, right? So we think about potential bounding boxes or local windows within this image. There are millions of them. Now the question is, how are we going to build this link that connects sort of regions within the left-hand side of an image to the concepts of these phrases on the right-hand side from the sentence description. Now, the simple idea is really the following, is that we have pretty good object detection models on the market, right? So what we can do is that, so how about we just run the object detector on the images? So the object detector will give us two things. First, it will give us these object regions in terms of these bounding boxes. And more importantly, it will give us the possible label of these bounding boxes in terms of these object categories. Right. Now, if we run the object detector on this image, so here's what we're going to get. We're going to detect all the persons, all the bikes, even though the scooter is also considered as a bike for some reason. We can detect most of the cars, and we are able to detect the concept of shirt, for example. Okay, now if you look at the left-hand side, we really have a bunch of bounding boxes with their labels. Now, it's much easier to match these bounding boxes to the right-hand side, which is a bunch of text phrases, right? So we can easily, probably not easily, but we can now leverage natural language processing or NLP techniques to do this matching. So we use either WordNet or text embedding, depends on what type of phrases we're matching. So that will create that will sort of allow us to get some sort of labels in terms of the link between the image regions and the text phrases. I saw something in the chat, but for some reason I couldn't. Well, I can. Yeah, so we just use a generic object detector that is pre-trained on open image dataset. So the object detector is able to detect over 600 common object categories. So it's off-the-shelf detector, right? Now, once we do this, we're going to basically match the object detector output to the phrases passed from the sentence that will create the pseudo labels. And then we can use the pseudo labels to supervise the learning of our deep models, just like we did previously. Right, here's our setting. During training, we assume that we have access to object detector outputs, right? And then we're trying to use these outputs to generate pseudo soft labels and use these soft labels to train our embedding networks. Now, during inference time, we don't assume that we still have object detection outputs. We directly use the learned embedding network to match the image regions to the textual phrases. So this joint work was Li Wang at UHK and Jing Huang at Google Research. We just published this at CPR 2021. Officially not yet published because the camera ready due is tonight, but we have this work down. It's already available on arXiv. If you're interested, you can find a older version on arXiv. All right, there's a question about this. What type of entities we're grounding? So we're grounding phrases that are defined as a single head noun with potential adjectives. So in this case, a child in a blue shirt is really two phrases. A child is one phrase, and a blue shirt is another phrase. Yes, so we're going to talk about this, how exactly we're going to do this. So the basic idea is actually very similar to what we just described. We're going to train this embedding network that on one side, we're going to embed the phrase features. On the other side, we're going to embed the image region features, right? Now, the challenge here is that we don't really know the correspondence during training, right? So here we have two levels of supervisory signals, or really two levels of supervision. At the top level, we have a matching score between images and sentences. It's shown at the bottom here. this is really trying to do a greedy matching between all the phrases and the regions and do a max pooling over the scores and using a contrastive loss here, right? To supervise this learning. So here we finally get rid of the triple ranking loss to use this contrastive loss, which is more stable and more scalable for training. Now, the second component is really comes from the idea we talked about, right? Assuming that we can have this region phrase soft labels or pseudo labels that are given by matching object detection tags to the head noun of the phrases, right? So we're going to have some sort of a soft target here. Now, instead of doing a multi-class classification problem, we're going to do a distribution matching, still using the cross entropy type of loss. So that's a second loss function, and I hope that helps to answer some of these questions here. So some of the technical details I would really refer to our paper, but I think I covered most of the key ideas. Well, let's take a quick look at the results. So here we're showing the grounding results in terms of the top one recall, or really the accuracy on the Flickr 30K datasets. So the green bar is our result, and the other colored bars are previous results, sort of weakly supervised phrase grounding. Now again, in this setting, during training, we only see images and its sentence descriptions. We don't really know the correspondence between the image regions and the sentence phrases. And during testing, an algorithm is presented with a pair of image and a sentence and trying to link the image regions to the sentence phrases, right? So our close competitor is this method called infoground. So when trained with the same set of data, our method is about 5.3% better in record. Even if they, you can train infoground with actual data, our method still outperform their method and all the previous method, including actually, I think this MATN from Yezhou's group. That's interesting. So to put a quick summary of what we just talked about. So we talked about some early work, almost 5 years old, on supervised image text matching, using this embedding network and triple ranking loss idea. It turns out that work has been widely adopted. It's pretty well cited and also widely adopted in the industry setting. For example, this is a block from Facebook engineering that talks about photo search function within Facebook. They do mention that they use part of the idea from our paper. Now, moving forward, we talked about this weakly supervised phrase grounding idea. The key idea is really to use the object detection to bridge the gap between image regions and sentence phrases. And our recent work, this weakly supervised phrase grounding, achieved state-of-the-art results on public benchmarks. So I'm going to pause here for a bit and see if there's any further questions. Okay, so I don't think we have any further questions, so I just move forward to our second component, sort of learning to generate scene graphs from image text files. Right, now again, we're going to go back to this sample image here, right? Here we have image, we have the text description, we don't have anything else. And we just present a model that can learn to ground these phrases into image regions. But if you really look at this text description here, it does have way more words than just the phrases, right? For example, we have all these predicates here, like a group of children playing on the street, right? And then, some on bikes and some on scooter, and, with bullshit and working, right? So what if we further parse these sentences into, subject, object, and predicate? So this SVO triplet, subject, sort of predicate and object triplet, that encode some sort of knowledge within this sentence, right? So we can decompose that sentence into a number of triplets. So here we have a group children playing on the street, some children on bikes, some children, one children on the scooter, one children in a blue shirt, and one children working on the street. The same children in a blue shirt is also working on the street. Now, the question is, can we detect these relationships between individual concepts? Right? So previously, we were really talking about sort of localizing these phrases, but now can we actually figure out what's the relationship between these phrases? So this task is called single graph generation. Now here, this is a more challenging task. Now here we assume that the algorithm is presented as only an input image, right? And it's tasked model is tasked to generate a graph, a graphical representation of objects and their relationships from this input image. Now here, a graph is defined as follows. It has nodes as objects, representing objects in the image. So these objects are actually localized. So you can think about each of these object nodes really as a bounding box in the image domain that comes with the label of that object. Now, between a pair of objects, right? So there's weights sort of between this pair of objects so that define the relationship between the objects. Right? So the scene graph is a directed graph. That means that so you cannot easily invert the edges, right? So let's take an example like men wearing glasses. The other part, if you sort of trying to invert that, it becomes glasses wearing men. So that's not a valid relation, right? So this is a directed graph that encodes all the possible relationships, hopefully, within the image in terms of the subject, predicate, and object triplets. Right. So previous works, single graph generation can be roughly divided into two parts. There's this fully supervised approach. While during training, they assume that the model have access to both the image and the localized scene graph, sort of manually annotated by humans. So there's a recent paper in Subject 20 that looks at this weakly supervised setting. While during training, the model is presented with only the image and a unlocalized scene graph. Now here, the caveat is that someone still have to annotate the scene graph from the image data. It's just that you no longer need the bounding box for each of the node on the scene graph. Now, so here's what we propose to do. We propose this language supervised setting. In the training, we only have access to image and its text description. Right, so we have image and the image captions. We have the image and image captions. Can anyone still see my screen? Because I have this warning saying, please move this window away from the shared window.
We are seeing that as well on our side. Please move this window away from the shared window. Did someone annotated your presentation?
No, I don't think so.
Then it's fading away right now.
Okay, well, it's coming back. So let me stop sharing just for now.
Yeah, let's retry that. Thanks.
At the same time, I'm going to mute my email box. Oh, I see. That's even more annoying. Let's try again. how it works.
Awesome.
Okay, let's get back to this. So basically, we propose this sort of language supervised setting. We're trying to learn a model that can detect the scene graph from image text files, or really by learning from image text files. Okay, again, so the key idea here is very similar to our previous work. So what we're going to do is that we're going to sort of try to save our algorithm from complete failure by running object detection on the input image. Now, again, what we're going to get are going to be a bunch of bounding boxes with their labels, right? So very similar idea. Now we need to match a pair of these bounding box to each of this triplet, right? So what we're going to do is that we're going to match the subject of this triplet to one of these bounding boxes. We're also going to match the subject of this triplet to the other bounding boxes, right? So we're matching bounding box pair to each of this triplet. And that will allow us, again, to create this soft and pseudo labels, right? So here we're using NLP techniques to compile their text embedding and sometimes compile their distance on the word net. So that will give us a soft score to say how similar the subjects are and how similar the objects are, right? So that's really the key idea. And by the way, this is work done by my student Yu Zhang, who is a third-year PhD student in computer science here. And this paper is currently under review. So here's how exactly it works. Our algorithm works. What it does is that during training, we collect all these image sentence pairs from external image caption dataset, including the largest one, conceptual caption and coho caption. Right here we have the image and the corresponding text descriptions. And sometimes we have multiple descriptions of the same image. Now we're going to use object detector to bridge the gap between these sentence descriptions and image. Now we're going to do object detection on these images to get the bounding box of the objects and the tag of each of the bounding box. We're going to run a language parser to parse the triplets from these sentence descriptions. So this, everything is off the shelf. The object detector, again, we use the open image detector that is able to detect over 600 object categories. The language parsers from Stanford that allow us to parse multiple triplets from a sentence description. Now we're going to do this label assignment step. Again, almost exactly the same idea. We're going to match. Now we're going to match a pair of the detected objects to each of the triplet, right? So now we match the subject to subject and the object to object. And then we have two scores, and then we're going to weight the scores to generate some sort of pseudo or soft labels for the region pairs and the triplet. Now we have a pair of regions that is best matched to this particular triplet. We're going to consider that as our supervisory target or supervised phase signal, right? Now here we plug in our model that takes a pair of regions and some contextual features like in this image and trying to label or trying to really classify the triplets. Here we're trying to classify the subject, the predicate, and the objects. Now, during inference, what we do is that we're going to, again, run the object detector. We're going to enumerate over all possible pairs of these image regions and send them to our model. And each of them will create a triplet. I'm going to aggregate this triplet all together to form the final scene graph. So a bit more details on the training side of the model, and also on the designer model to some extent. So here, what we get is that we get a pair of image regions. Now record that this is from object detector. So that means that not only we have these region features, right? We also have these object tags associated with these regions, right? So here we have the person, and that's the tag of this region. We also have shape, the tag of this region. Now we extract text features for these object tags, and we extract visual features for these object regions. So what we do is that we further encode all the rest of the regions into some sort of contextual features as an actual sort of feature into our model. And then we train this vision sort of language transformer. So what it does is that it's really just a vanilla transform model that takes, almost like takes two parts of the input. On one part, we have the input text tags from the object detector outputs. On the other side, we have input visual features from the path regions and also contextual features from the rest part of the images. And now what we're going to do is that we're going to ask this model to fill in the gap of what is a predicate here. Now, so here, the ground truth predicate is given by this assignment process, right? So here we just assume it's going to be drive, even though this can be quite noisy. And then we're also going to ask this model to output the subject and object in the sentence. So this is because our detection tags and the sentence tokens can be quite different. They might be lying on, they might be a different dictionary, right? So here we detect, the object detector tells us person and ship, while the sentence token tells us man and boat. We're just trying to use this sort of a triplet transformer network to predict, to fill in the predicate and trying to correct the subject and object names. So very simple idea. And during inference, the key idea is that we're going to basically enumerate every possible pairs, right? Now, let's say, so with the object detector, we have three objects here. We're going to take the first pair, right? Send this into the model, and our model will predict, men on motorcycle, right? So that becomes a triplet. Now we're going to take a second pair, right? So that produce another triplet called men wearing helmet. And then we're going to aggregate these two pairs together, stitch them into a graph. So that's a key idea of inference. This model does have a much higher inference cost because you have to enumerate all the possible object pairs and so on as well. Besides, it does use a transformer model that's slightly more expensive than a convolutional neural network. But overall, it's still quite efficient. You'll be able to return the result of a single image around a second or two. Right. We're going to briefly, just very briefly touch base the result side because we still haven't published this side, but I'm very excited for these results. So here we're trying to evaluate this single graph detection, which is a very challenging task. Now, in this case, in the test scenario, the model is only given a single image and is asked to output a localized and categorized single graph. Localized means that you have to identify all the regions on the image and also label these regions correctly and also identify the relationship in the right way. So the metric we use is this record at 100. So this is a mix between classification and detection. So let's consider a single triplet. So a triplet has been labeled as positive only if both the subject bounding box and the object bounding box overlap with the ground truth that is larger than the certain threshold. So that part is detection, right? So basically you have to detect both the subject noun and object noun right. And also we have to classify the predicate and right. You have to get that classification right. So it's a classification plus detection problem. So it's quite challenging. Now, what we can do is that we first train our model on this sort of fully supervised setting, and this is the upper bound of our model. It's really, it's about 15.3% for top 100 core. I think this is also slightly higher, or at least on par with many of the state-of-the-art supervised single graph generation methods. Now, this is the latest method, or the latest result from weakly supervised SIMGRAPH generation, that they do require a unlocalized but still manual labeled SIMGRAPH. So the record drops from 15.3 to 5.4. And here's our result, right? Here's our model trained using only image captions as the training signal, but we do use actual object detector to be fail. Now our result is about 7.0, that is already higher than this weakly supervised method. Now, if we compile directly in this weakly supervised setting, meaning training our model using unlocalized SIMGRAPH, so this is what we are getting. We're getting almost doubling the numbers here. So here are some of the visualizations of the results. We're comparing these quantitative results from our model, yet trained with different settings. So we have this fully supervised training, requires localized SIMGRAPH. We have this weakly supervised setting in the middle, requires unlocalized SIMGRAPH. And finally, we have this probably weakest form of supervision that only requires image caption data. So if you take a quick look at these results, then it seems that the model trained with image captions produce relatively sparse graph. They just have less edges, right? They will have very similar set of nodes because this is all based on the same detector output. Now, it's probably not desired that we just detect less of these relations, but if you really look at this carefully, in this fully supervised setting, a lot of these relations are a little bit weird, actually quite biased by the way these data sets get annotated. This is probably best illustrated by this example here, right? So for some reason, this model trained on the fully supervised setting really just output two different type of relations, like it's either in or on. While our model learned from this image captions does produce sort of more diverse set of relations. So we have has, of, with, and some other stuff. So what we realize is that, so for the current SIMGRAPH data set, it turns out the number of predicates is relatively small. So I'm not really sure if it's a bias in the annotation process or really a bias of how we tend to describe the relationship between objects. But anyway, this is what we observed just from these quantitative results, that our graphs are oftentimes sparser. We just have less relationships. Our model just detects less relationships if we learn from image captions, but our model does able to detect a diverse set of relationships between these objects. Quick summary. So we present the first work to demonstrate that learning SIMGRAPH generation from only image text files. And our model outperformed the latest model in this weakly supervised setting and this language supervised setting. So a quick overview, again, quick summary of the results, a quick summary of our setting. During training, we only have access to image and their language descriptions. We assume we have additional access to an object detector. During testing, we have image and the object detection results. Our goal is to generate the SIMGRAPH at this time. So I see we have a number of questions popping up, so I'll just pause here and try to answer some of them. Oops. Well, there's just too many of them. So I'll start from the latest. Can we, the question is, can we pre-train the model to learn the types of possible edges between the objects, such that the SIMGRAPH can be generated without caption and can be useful for different vision tasks like VQA? I'm not totally sure about what's the scope of this question. Is it more about just trying to constrain the potential relationship between objects, or is it something different? So in our submission, we showed two different settings. We showed a closed set dictionary setting. Basically, we only consider sort of predicates and objects that are presented in the target data set. In this case, our target data set is viral genome. We also demonstrate a open set setting where we don't put any constraints. We just create a dictionary from all the possible tokens on the caption data set. And then during inference time, we're trying to do a matching between our caption dictionary to the target dictionary. And we show that the open set setting is definitely more challenging, but can still work. Actually, somehow surprisingly, the open set setting does help to improve the performance, especially for the categories that are less frequent on the target data set. Okay, so another question is that assume that the relation of the PEL can be empty and some prior knowledge can be used. Yes, we do assume that the relation can be empty. So in terms of prior knowledge, I think a lot of people are trying to incorporate knowledge graph because you can easily mine this knowledge graph from internet, mine this SVO PELs from internet. I think that can be something interesting to look at. So another question, even though the object detector detects the helmet as hat, it could generate helmet in the scene graph. Why is that? Well, this is because our target signal is really the tokens passed from the sentence, right? So our vision and language transformer really trying to classify the predicates and also trying to correct the object detection tags. The other question is, I noticed that you're grounding some of the words like some and one. Is coreference also involved? Actually, no. We didn't really consider coreference. Actually, we have some visualization showing that this coreference case is actually quite challenging. If you have multiple instances, from almost the same object category, then you will have this challenge of referring expression. Sometimes it's not totally clear, which of this phrase is referring to, or even which of the triplets is referring to. Do you match a single phrase to multiple bounding boxes? Currently, we only match a single phrase to a single bounding box. And we do this using a sort of greedy matching. Okay. I think that's about all the questions here. So let me move forward to spend the next 10 minutes or so, or I'm running slightly out of time. Spend the next 10 minutes or so to switch gear and talk about this image capturing task. This is actually, I think one of the audience asked a question, can we use this for downstream vision and language task? And I hope that my last part of the talk will cover this question. So here we're considering this image capturing task. So the idea is that given image, we're going to generate a text description of this image. So a lot of people are, a lot of researchers focused on generate accurate or high quality captioning. Some of the more recent research look into generate sort of diverse captioning, trying to cover different components of this image. And more recently, there's this trend of research that looks into grounded captioning. It means that it not only generates the sentence description, but also link the tokens of the sentence back into the image domain. And also there's this controllable captioning or controlled captioning idea. The idea is that if I only present a subset of regions within the image, the model should generate a caption that focuses on this particular component of this image. Right, so there's a bunch of work for image captioning, as you probably know. Some of them focus on the quality of the caption, some of them focus on diversity, some of them focus on controllability. So we present this work that is already published in the 2020, again from my excellent PhD student, Yu Zhong, that present a single model that is able to generate multiple captions from a single image. And these captions are also grounded. So we're generating multiple grounded captions from a single image. So our model also has this capacity to be able to take a set of regions as input and generate descriptions that are focused on these particular regions. So we have a single model that is able to deal with sort of accurate captioning, diverse captioning, grounded captioning, and controllable captioning in one shot. So that's why we call this thing comprehensive image captioning. So how we can do this? We're going to use this idea of SingGraph, and finally, that's a link, right? So what we're going to do is that we're going to first pass this image into a SingGraph structure. So in our ECV 2020 paper, we use existing SingGraph detection method. Now in our most recent work, we sort of plug in the SingGraph detector that is learned from image captioning data or image tag spells. So what we're going to do is that, so imagine we're taking this image that might have multiple components. This component about a person driving a boat on the river. There's also a component about several persons sitting on a bench on the bank of this river, right? So what we're going to do is that we're going to take this SingGraph and trying to identify different components within this image. The way we're going to do this is we're going to decompose the SingGraph into a set of subgraphs, with each subgraph representing a component within the image. So for example, we have men on the boat, we have people sitting on the bench, in this case. Right. So specifically, what we do is that we take the whole SingGraph and really chop them into many, many subgraphs. So here, I think we use existing sort of graph partitioning method to chop them into almost like hundreds of these subgraphs. Now, not all these subgraphs are meaningful, right? So what we're going to do as a first step is to try to train a model to identify the meaningful subgraphs that represent, a component or a semantic component within the image. And then, so we're going to leverage this model to select a small set of subgraphs from a large set of subgraphs and only decode these small set of subgraphs into the sentences. Just a bit more details for the graph decomposition. We use this method from the machine learning research paper, GMLR paper, that really, you can think about this as almost like a neighborhood sampling strategy. I start with a random node and trying to do a little bit of random work from that node until it terminates that identify a subgraph. And, you start this process again, start from another random node and do a little bit of random work, and then you find another local subgraph. And you do this many times, you get hundreds of subgraphs that are different to some extent from each other. Right. Now, so here's how we actually identify meaningful subgraphs. So what we can do is that we're going to find those subgraphs that can be matched to ground truth captions. Now, the assumption here is that we have access to multiple captions that are that potentially describe different components of the image. Right. Now, what we're going to do is that we're going to match each of the subgraph to every possible caption within annotation during training. And then we're going to select these subgraphs. We're trying to learn to select those subgraphs that can be matched to at least one of these sentences. Okay, so here we use intersection of union score to match the concept lies on the subgraph to the head-noun tokens within the sentence. Right. So again, we have this 0 and 1 matching score. Now we're just going to design a binary classifier to classify the subgraphs. So what we do is that we design a graph neural network that's trying to take these subgraph features as input. So here we have the visual features and text features on each of the node. We also have these edge features. And we're going to train this graph neural network and in combination with a Martian linear perceptron plus a sigmoid normalization function to form this binary classification problem, right? So this binary classifier will just look at each of the subgraphs and try to see if this is meaningful or not. So this is more like a selection process, right? So now what we do is that we first have this, we have this large set of subgraphs. We're going to run each of these subgraphs through this, selection process. Some of them will have pretty high scores. Some of them will have low scores. And we only focus on those subgraphs that have high scores. And then we're going to build a graph, almost a graph-based LSTM model, trying to decode this particular subgraph into one of the ground truth sentence captions. Now here, this is almost exactly the same LSTM adopted from Peter Anderson's paper, this bottom-up and top-down attention paper. The only modification we did is to allow this LSTM to consider the graph structure at the very beginning. Now, the beauty of using this LSTM is that we can use the attention mechanism to really backtrack those tokens into the graph node or the input graph node, right? So that's how we can generate those sort of grounded captions. Right. So here we know that this man is from this man here, this boat is from this boat here, right? So that's how we generate this grounded captions. Now putting things together, so given the input image, we first convert this image into a scene graph using existing or our own scene graph detector or scene graph generation method. We're going to process this scene graph using this graph neural network to create features on the node and on the edges. Now we're going to sample subgraphs from this scene graph, just chop them into lots of subgraphs. And we use this selection process to re-rank these subgraphs. And only those subgraphs has pretty high scores will be decoded using this attention-based LSTM, and that generate each of the subgraph will thus generate a unique caption. And because the way we sort of sample the subgraph, so it's very likely that the captions will be quite different because they're derived from different components of this graph that representing different components of the image. So again, some of the quantitative results. So on the left, I'm showing you the input image. On the middle, I'm showing you the full scene graph that's been detected. So here are the full scene graph with the grounded regions. Right. So if you take the full scene graph, this is what you can get from just decoding the full scene graph. Now, what is interesting is that we can take any subset of these scene graph and trying to decode different components of this image. For example, if we take this one, we can decode them into the sentence, a man and a student is walking down the street. Now the same image, now a different subgraph, and the grounding of the subgraph, then we ask them, the model to decode from this particular subgraph. Now, what we get is that a bus is parked in front of the building, right? So now it's exactly the same image, but we're trying, our model is able to detect very different components of this image by doing this graph decomposition and decoding steps. Another example here, the same idea. On the left, I'm showing the image and the localized box of the subgraph. In the middle, I'm showing you the subgraph sample from the entire scene graph. And on the right, this is the caption output that is also grounded. So If you're really careful, you might notice a few typo here. For example, in a orange hat. So I was asking, my son, why do you have this typo? My son say, okay, well, this is decoded from the algorithm. I don't really know what's happening. So that's technically it's not a typo. That's just algorithm output. Okay, so quick summary of the results. So there is a trade-off between the diversity and accuracy. So if you look at all these method optimized for accuracy, the CIDR scores is around 115-ish. If you look at all the method designed for diverse captioning, their accuracy is around a little bit more than 100, but they do have more diversity in terms of the 2-gram diversity. So this is where our method lies in, right? So here we have different re-ranking strategy, or really different post-processing strategy, that we can tweak our model to be either more accurate or more diverse. And this is where we are, that we have a pretty good balance between the accuracy and diversity. We can be quite diverse, that more diverse than all these previous methods, and actually more accurate than them. We can also be quite accurate, that is very close to these accuracy optimized models, but still maintain a certain level of diversity between the generated captions. So this is about diversity and accuracy. And then this is the grounding results. The take-home idea is that we do have better grounding results than many of the baseline methods. We have, I think this is the F1 score, with much better F1 score. Now, of course, this grounding is also very challenging here. And now finally, the controllability scores. So this is the controllability setting. Well, the model is asked to decode a target sentence given a set of input image regions. Here we have 2 metrics that measures both the CIDR score of the decoded sentences, and also this what are you score to map to really figure out if the sentence really focus on the concepts that are presented as input to the model. So again, we have better caption quality and better sort of concentration on the desired concepts. To summarize, we present the first comprehensive image captioning model that enables accurate, diverse, grounded, and controllable captioning at the same time. State-of-the-art results across a number of captioning tasks. This is already a published paper, so we do have a project web page and a code repository. If you're interested, feel free to try it. So I think I'm almost running out of my time. So I'll just bring back this first few slide and trying to convince you that we have freely available image text files, a lot of them over the internet, that presents this unique opportunity for learning visual knowledge. That's I'm primarily interested in. So moving forward, we're trying to work on the grounding of egocentric actions. This, our group have been working on this egocentric video understanding. So here the idea is to ground a video of many different actions to the instructions provided in the text format. There are other things that my group is doing, including this first-person vision, surgical video analysis, and also we're very interested in designing some of these durable sensors and sort of durable computing systems. You can find more on my website. And finally, I'd like to sort of really end my talk with a nice demo. There's a recent paper in collaboration with Cornell University where we designed this smart wristband with 4 tiny cameras, thermal cameras embedded, and we're able to recover the full degree of hand pose. Move forward, a real demo. So device and real-time processing of this thing, reconstructing hand pose, superimpose from the first-person perspective. It's not super accurate, but quite reasonably accurate, even with an object in the hand. With that, I would like to conclude my talk by thanks all my collaborators, especially my longtime collaborator, also my PhD advisor, Jim Ray from Georgia Tech, Chen Zhang from my close collaborator Chen Zhang from Cornell, Li Wan from Chinese University of Hong Kong, Sarbachi from Purdue University. And that's really the end of the talk. So I would like to conclude with this nice image. Title was Spring of Deception that is captured about 2 weeks ago at our campus. So we have quite a bit of snow here, and we're probably going to get a bit of snow during this weekend. But thanks again for coming to my talk, and I welcome all the questions.
Thank you, Ying. I saw exactly the same robot on ASU campus as well, just last week.
Yeah.
Trying to launch the food delivery service. Let's see if we have any other questions from the audience. Really interesting talk, and many of the directions actually kind of share a lot of same spirit as we are trying to do. One of our students, Tijas and Pratya, they are trying to use image captioning to train VQA systems in a purely self-supervised way. An archive version already online, and the other one is under review currently. We show that purely rely on image caption, you can actually train a quite well-performing VQA model as well. If there's no other questions, I would like to start with one comment as well as a question regarding the evaluation you are doing with the scene graph matching. Since you are using image captions to ground the image, right? Mm-hmm. And when the people annotating the scene graph and compared to annotating an image with a sentence, I would assume the caption will be a bit more diverse with the word choices, all that, right?
Right.
So that also leads to your observation that your methodology have generated scene graph with much more diverse word, especially verbs. Mm-hmm. Now that leads me to wondering if you are comparing that to the annotated ground truth scene graph, does it even do the justice for your methodology? Your methodology probably is actually performing much better as a methodology generating scene graph with diverse verbs, but not being well appreciated, comparing to the ground truth that is annotated by human being while they were asked to annotate scene graph.
Mm-hmm. I think we see some example like that. So one thing is that the scene graph evaluation does have different metrics. So what I put in the slides is the most challenging metric that you have to get both the subject, predicate, and object all correct, and also localize the subject and object. But there are other metrics that looks at, for example, if given the bounding box, can you classify the subject and object correct? Or given the subject and object pile, can you classify the predicate correct? Mm-hmm. So I think we have some detailed results in the paper or in the submission that talks about some of that. I think some of these metrics does capture the case while a model get pretty good accuracy for recognizing the subject and object, but not so good at recognizing the predicate. Just because you mentioned the ground truth predicate might not have sufficient diversity. So currently we don't really have a great solution to that. I mean, I would really consider that as a limitation of the current generation of the data set. Mm-hmm. I think there's some ongoing effort to really push the limit of the scene graph. I think Feifei's group is trying to work on this, really just creating a larger scale scene graph data set that is done in a semi-automatic way. So I think I would really say that we don't really have a solution, but moving forward, there might be just a better data set down the road.
Of course, the reason why I ask the question is we are also looking into the evaluation matrix, especially the evaluation matrix for captioning, as well as scene graph generation, to see if they actually do the justice for all sets of methodologies, especially considering the diversity of the captions, diverse caption you want to generate, as well as the focus of the caption, focus of the graph should be weighted higher while you're doing the evaluation, right? So for example, the foreground of the image should be better captured compared to the background of the image, which is considered as the peripheral. So some of the ideas we are trying to develop. I'll share with you some of our work as well after the talk. I think they can find synergy among them as well. Any other questions from the audience? Because many of our audiences are actually working in vision and language space. Tejas, you would like to?
Yeah, so I had a question about scene graph generation where you've used captions as inputs. So could the same quality of scene graphs be generated if you use captions that were predicted by some off-the-shelf caption detector? So the reason that I'm asking this is it seems that captions generated by caption generators are usually grammatically maybe not so great, or maybe not diverse enough, but they usually capture the objects and actions being performed in the image. So would that transfer well to scene graph generation?
We haven't really tried that. That can be an appealing idea. But so my personal impression is that I think human annotated captions is still of better quality than machine generated captions. So now I think there is one setting that I did not present here, is that we consider training using different data sets. So there's conceptual caption data set and COCO caption data set. Now for COCO, we actually filtered out those images that also have, appears in visual genome. It's a minor detail. But for COCO, those captions are provided by human, and you have multiple captions per image. And even though COCO is much smaller than conceptual caption dataset, we observe better sort of performance was training on COCO. Now for conceptual caption, my understanding is that it's semi-automatically annotated. It's not completely, human annotation of the caption. It's also not completely machine generated or harvested from internet. It's some kind of mix in between them. So we did see a slight decrease in performance.
I see.
As a function of the caption quality.
Okay, that's interesting because that opens up maybe avenues if you can transfer scene graph generations trained on human annotated data sets and then perform inference on, let's say, conceptual captions. Okay, thanks.
I think following up on what they just said, so it's important that the data set that you used, the captions were of a particular kind. So if you take off captions from the wild, I think we had a talk recently where when people caption an image or have a label below, they kind of use information actually only known to them. In the sense, it's like a basketball player, they would know the name of the basketball player or some more information that is very hard to get it from the like some other person to understand from that image. So I think the particular data sets that you use had very good captions.
I see.
Or you have to do some, otherwise you'd have to take the caption and kind of neutralize them in some aspect or make some changes to the caption.
I see.
Code mapping.
Yeah, that reminds me the VLN work presented by, they are trying to basically translate the specific mentions to the item to general mentions, and then train the model.
I think we're lucky that I think conceptual caption data set really did that. It's just trying to neutralize the tokens within the data set. So that's we probably benefit from that part. I didn't really realize that part until today. Lessons learned.
But I mean, you gave a very good talk and good work, very excellent work. Thank you.
Thanks.
It seems you're at your place, it's getting dark. because we can track from the window. It's already.
We're 7:40-ish p.m. I mean, anyway.
Yeah. Are there any other questions from the audience? If not, let's thank the speaker one more time. One last comment. I assume I'm actually speculating this robot that delivering food on our campuses are teleoperated.
Yes, you're absolutely right. I think into the news is all teleoperated.
It's actually a stop from Ukraine. So they might hire a huge human farm. They're operating all the robots on campus. But that's still a challenging question, right? So if you only have 100 people, you need to control, let's say 10K fleet. And it becomes a scheduling problem. Certain robots can move autonomously. Certain may get into critical situations that you need to take over by a human operator. Anyway, that's just a side thought. Thank you for joining today's session. And
thanks for the invitation, and I enjoy all the interactions.
And I hope we can meet in person sometime later this year or early next year during our conference. We should catch up.
Sure. All right. Talk to you later.
Thank you.
Thanks.
Thank you all for joining. See you.
See you. Bye.
Bye-bye.